Go live. Alright. So welcome back. Hope y'all had a good spring break. And let's get right into it. So today we're working on generalizing our left values. Before the break, the last thing we did was we wrote some optimizations for arithmetic expressions and for stack allocation. So we can see here that we've got this arith test file. It's got 501 lines in it. Without any optimizations, the generated LVM file comes out to about 19,500 lines, but with our optimizations, it comes down to 524. So that is a very good size decrease. That's what we wanted. But what's next? So we are at a crossroads. We can add a bunch of things right now. We could add operators. We could fix our functions. We could do a lot of things. But I would like to add arrays to the language. But we can't do it yet. There's a few things we have to do first. So we need to first be able to scale pointer offsets. So imagine you've got this array 0, 1, 2. You've got this int pointer that's pointing to it. If you use the value x plus 1 in something, most C compilers are going to convert that to be x plus 8 actually, because they're assuming that you're trying to access whatever that's pointing to and then the next element. So it's going to extend that 1 or 2 or whatever to, it's just going to multiply it by the width of that data type, because it's assuming that you're doing array accesses. So we need to be able to do that, and we haven't done that yet. I'll get to that in a second. We need to change how we use left values. They need to become more dynamic, and that way we can actually do array accesses. So if we've got x that's pointing to some y, and we don't want to say like y equals 5, we could say star x equals 5, and that's going to say get whatever x is pointing to, sorry, this should be int pointer x. Get whatever x is pointing to and assign the value 5 into that container. Right now we can't do that. And if you look at array syntax, the bracket notation that you're very comfortable with, hopefully, that's actually a shorthand for using pointer accesses like this, and in combination with the pointer offset update that I mentioned before. And then the third thing is that functions need to be finished up. They don't really need to be finished up before we do arrays, but I'd like to do it because I want to be able to call malloc and get rid of our print statement. And we've just been sitting on that for too long, so I think we're going to do that before we get to arrays. And so we're going to start with number 2. Pointer offsets are going to be kind of hard to test because LVM does not guarantee that if you say int x semicolon, int y semicolon, there's no guarantee that x and y are going to be next to each other in memory. So you're just going to be accessing random memory. There's not really a good way to test that. So I imagine that will be part of the arrays lecture. So this is our goal. We want to add support for this test. So we declare 3 integers, a, b, and c, and then we do a multiple assignment, which we have not supported yet in our language. We're going to say a equals b equals c equals 3. And this should initialize all 3 of those variables to have the value 3. Next, we declare an int x and an int pointer y. We will say that y points to x, and then we will say that the contents of what y points to should be set to 5. And then finally, we are going to make a double pointer z, which is going to point at y, which is a pointer in itself. Then we are going to double dereference z. So we're going to say whatever z is pointing to and whatever that thing is pointing to, store 19 into it, which should be x. So in that second to last line, we don't mention x at all from the previous print x statement, but we have modified the contents of a pointer to x. So x should change, and we should be able to print out 19 in that last line. And I was hoping, when I was writing the code for this lecture, I was hoping that we would also be able to do something like declare a double pointer q. Q also points to y. And then the thing that q points to should now point to a. And then we'd be able to say star y equals 7. So take whatever y points to, which should be a, stick 7 in it, and then print out a. But we've got this frustrating bug issue that I will probably talk about at the end of the lecture. So in the test, in the code, I've added that case, but it's all commented out. And in the future, we will uncomment it. But if I'm correct in my intuition, I think that when we add local variables, that bug should resolve itself. So this is the plan. We need to restructure our assignment statements by converting the assign token to an operator, because right now it's been a keyword basically. So it's got a very concrete, idea of how it can be used, and so we'd want to make that an operator. So because operators are more versatile, they deal with sub-expressions, they can be manipulated and whatnot. We want to add right associativity to the Pratt parser because assignments should be right associative, and we'll see why. We will update AST nodes so that they can be designated as either L values or R values. And then, of course, we need to update the code generator so that we can support all these new features. So, the first thing that we want to do is we want to make assignment an operator. It's like I said, it's been a keyword up to this point, but making it an operator is going to let us chain it, like we can chain 1 plus 2 plus 3. Those plus operators are chained. So if we want to be able to do something like x equals y equals z equals 3, we need to generalize our idea of what an L value is. That way we can treat assignment as an expression and an R value rather than a statement in and of itself. And so in that example that I gave, originally we would have said x equals 3, y equals 3, z equals 3. And x, y, and z all would have been left value identifier nodes in our AST. But now x, y, and z are all going to be labeled as just plain identifier nodes. However, y and z are going to be marked as R values. And so that's going to tell our compiler down the line, hey, after you do the assignment, return the value of what it got assigned to so that I can stick it into something else. So that's neat. And then using assignment as an operator is also going to allow us to generalize what appears on the left side. So it's not just going to be an identifier. It could be a dereference of an identifier, and that will allow us to assign to pointers and whatnot. So, got the code open here. Oh, why did that go back to the screen? Let's see. So, value. I don't want that yet. Okay, so I'm just walking through where I've replaced the L value identifier stuff. So now, in assignment statements, we're just going to make an identifier node. We can remove our left value identifier token altogether. We're not going to use it anymore. Where else? Do we do anything else with it? Nope. Oh yeah, and then we took out the L value identifier case in our code generator, but we will replace it with something. Yeah, I guess that's not much code yet. In our AST node, I've added this is our value field. It's going to default to false, which might seem a little weird because most of the expressions that we deal with, at least half of them, and by definition, greater than or equal to half of them should be R values. But the reason why we assume it's not an R value at first is because imagine you have x equals y equals 3, and you're parsing it left to right. You start with x, and by default, you don't know if it's an L value or an R value. You could just have a statement that says x plus 5 semicolon. Per the way that we're updating our L values, that would be completely valid. You'd be able to have a statement like that doesn't do anything. And C lets you do that. Clang lets you do that. It just gives you a warning. But yeah, you start with that x and you don't know whether or not it's an L value or an R value until you hit the first equal sign. And then you can definitively say, okay, what I just looked at is not an R value, so we're good. But consider if we had assumed that it was an R value. Well, I guess you'll see in a bit how the way that we wrote our Pratt parser, it would require that we do another tree traversal to go back and un-R value all of the stuff that we had just parsed. So it just makes a little bit more sense to default the R values to being false. And again, we'll see why in a bit. Don't worry about all this stuff. Just treat is R value like a regular bool. This was my attempt at fixing that bug. It didn't work yet. And if you uncomment this code, it breaks everything. So I'm going to fix that in the future. I'm not going to worry about it right now. And so the next thing we do in converting our assignment to an operator is we add it to the operator table. Where is operator precedence? Oh yeah. First of all, I noticed that I mislabeled all of the equality operators, but that's fine. So we've added the assignment token to our operator precedence table, which means our parser is automatically going to recognize it and parse it for us. You'll notice it has a very low precedence, so it's going to be parsed last out of everything. And then you'll also notice that I've added this right associativity operators list, which for now only contains the assignment token, but it'll have more in the future. But first let's talk about right associativity. So consider this statement, x equals y equals 3. On the left we have a left associative assignment AST, and on the right we have a right associative assignment AST. I've labeled them bad and good. Can y'all figure out why the bad one is bad? Hopefully at this point you should be familiar enough with the compiler to pick out why this would generate the wrong code, why it would parse, why this is not a correct parsing. Any ideas? First thing that comes to your head?
Because y doesn't have a value yet. Yeah.
Exactly, yes. So the way our code generator works is that it does a depth first traversal of our AST. So it's going to go straight to that left branch, and it's going to set x equal to y. And they do have default values. Everything's default initialized to 0, but that's going to say set x equal to y. So x and y are going to be, x is going to be set to 0, and then that thing on the left, like, what is that? Why am I trying to set it equal to 3? That's not any kind of value that I can assign to, right? That's a sub-expression on its own. You can't assign to a sub-expression. So in a right associativity context for assignment, we would do the thing we want first. We would go right to left. We'd say first y equals 3, and then we're going to go back and we're going to say, okay, well, forget the thing about the sub-expression because illustrated it poorly. But set y equal to 3, and then set x equal to the return value of that sub-expression, which would be 3. So we're saying that assignment expressions evaluate to what the assigned value was. So if you say y equals 3, that little sub-expression is going to evaluate to 3, which should make sense, right? That's how, if you use inline assignment in C, which you probably shouldn't, but if you do, that's what you would expect it to do. And you'll notice that basically the only thing I've done to make it right associative is I've swapped the leaf nodes. So they've just been mirrored left to right, and as it turns out, that's a perfectly good way of doing it. Is that cool? Does everyone get right associativity? Okay. So adding it to our prep parser is not that complicated. Basically, all we have to do. Why does it keep going to the other screen? All we have to do is update our loop condition. So before, all we wanted to do was check if our previous token's precedence was less than the current token's precedence. Now we're going to add this disjunctive clause that says, it could be that, or it could be that the precedence of the current one is equal, and this is a right associative operator. If you'll remember when we first did prat parsing, I told you I'm not going to cover why any of this works, but you can trust me that it works. So that's the way people add right associativity to prat parsers. It's a general solution, so you can trust it, and it does work. So, however, that's not the only thing we need to do. We need to do some special checking for the assigned token, because we don't want to swap the children of every single right associative operator. For example, the exponentiation operator, even though it doesn't exist in C, in Python, for example, it is right associative. You don't want to flip those arguments because you're going to get a completely different answer. So in the case of an assigned statement or an assigned expression, we will want to swap the left and right children of our node, and that's just going to do exactly what I just showed y'all. Otherwise, and here we're saying that the left value is going to continue being an L value, but the right value is going to be an R value. I don't know. It seems obvious, I think, right? The thing on the right side of an assignment operator is an R value, and by default, the thing on the left side is not an R value. It can be changed in the future, and we'll see that in a second. But anyways, otherwise, if the node type is not an assigned statement, which is every other operator that we've dealt with, then we're obviously dealing with an R value. The other places we need to set R value to be true is whenever we hit a semicolon or a right parenthesis, and then that happens. I guess, did I take that? Yeah, I took it out. Yeah, so, and then whenever we break the loop, which again, semicolon or parenthesis. So, whenever we see something that says we've been parsing an R value, then yeah, of course we want to set this thing to be an R value. So, let's do our code generator updates. Alright, so first thing you'll notice is that I changed the type signature of AST to LVM. Can anyone figure out why this thing is now only going to be a label value? I haven't told you. But consider how we're not explicitly dealing with L values anymore. Do you remember? Do you remember what this value was used for initially? I mean, it says kind of vaguely right here. We would pass a value from a left branch traversal to a right branch traversal. I'll tell you. So initially, that left virtual register getting passed into the right virtual register, down, is this the only place? No, right here. So when we did have our old version of the assign statement, or an L value identifier, we'd use those to store the right value into the identifier on the left. Right? Do we remember that? We would compute the left stuff. We would generate all the code for the left branch. We'd get a L of M value out of that. We'd pass it in the right branch, and the only time we ever used that was in the case where we were doing assignments, because we would compute the value on the left branch, and we need some way to carry it back over to the right branch to assign it to a variable. So that's what we used it as before, but now we're not doing that. We're not treating assignment statements like that big nasty thing. We're just treating them like regular expressions, so we can, I should say standard expressions. So we're gonna deal with them in a more.
Wait, does he have regex?
There's libraries, yeah. So yeah, we're just gonna treat assignment like a standard common expression from now on. We're not gonna do any fancy R value stuff. Although our compare and jump statements still do need a label carried over, so they're going to use that, and that's fine. But so the three cases that we need to update are whenever we see an identifier, whenever we see an assignment token, and whenever we see a dereference token. I did rename this because it was confusing, so thankfully. So looking at an identifier, so if the identifier is an R value, or we are dereferencing it, then we are just going to load that global variable. That's pretty fine, right? Like, we were already loading it in the case where it was technically an R value by default over here. And you'll see why we do that thing with the dereferencing when we look at that case. Otherwise, we are going to return none. And I don't think, so the reason we want to return none here is because it's not an R value, it's a left value. And we don't compute anything if we just have an identifier on the left value, right? So that's if we see an identifier. When we see a dereference operator, if we have an R value, we're going to do our regular dereference that we did before. Otherwise, we are going to return the left virtual register, which is the output of computing, of doing the left depth first traversal. Back over the top. The left virtual register is what we get when we traverse the left branch of the AST. And the reason we specifically return the left register is because the dereference tokens only have a left child. So dereference is going to do its dereferencing on the left child. It's going to return its stuff if it's an R value. Otherwise, we're going to defer to the identifier code. So it's a little all over the place. Yeah. Okay. And then finally, we've got our assign statement. So assign used to be really simple because the value of an assign statement was already computed in the right branch. So we could have just returned the right value, even though it was never used because you couldn't use an assignment statement like a value. But now, when we've got an assignment statement, we're looking for two subcases. We want to see if we're assigning to an identifier or if we're assigning to the dereference of an identifier. So if we're assigning to an identifier, we are going to do basically the same thing that we did when we used to have L-value identifiers. We're just going to store a global variable given the name of the variable and the thing that got computed to be stored into it. So that's not too complicated. But if we've got a dereference operator, this is a new case. This is our like star x equals 5. I've written this new store dereference code to handle this, and I would rather just show you the intended generation. So let me just do that. Desktop echo. Okay. We'll have int x, int pointer y equals end x, star y equals 5. Print x. So this should print 5, right? Do we agree here?
Yes.
Okay. Example temp test. Okay. So this is the code that got generated for that. So declare our x and y. We are going to, I'm going to open this in VS Code so it highlights.
Light mode.
I don't know, I got converted to light mode. I feel like it reads so much better for assembly. I don't know why. But,
This is the first time I've seen VS Code in light mode.
I think it's a nice theme. But anyways, so we get the address of x, we store it into this register 1. I think I have optimizations turned off, so all this load store stuff would get optimized, hopefully. I have to look into that. But main idea, get the address of x, store it into y. We saw that in the program, right? Here, so yeah, that's that part right there. Done. Now we are going to load y, which is going to give us the address of x. And we're going to store this integer 5 into that address that we just got. Does that make sense? And just remember that whenever you declare a global, it's always one more pointer than there's an implicit pointer. So x is an I32 pointer, so you have to store into it like that, right? Then we call printf. Boom, done. So the code, I'll just show you in here. Oh, I need to pull. Other dereference. There we go. So, destination and value. In this example, right here. So this is the statement that we're looking at, and this function store dereference is going to handle all statements like that. Destination is going to be the value of y, which is the address of x, right? And the value is going to be, in this case, 5. So value is not a register, right? It should have been, yeah, it's not a register. So I guess I can just take that out then. I don't know. We're going to do some register loading just in case we haven't already, because this could be y plus z or something. It doesn't have to be a constant value. And we are going to generate our store. It's going to give us that data type. So store I32. We are going to say its int value, which is 5. And then we're going to give it the we're going to give it the destination, number type, data type, all that, and then we give it the actual register value of the destination. So that's a simple case. Let me do let's do this. So this should print out 99, right? Okay. Let me make sure this actually works, because okay, I'll fix that bug tonight probably. But the goal was that would trigger this branch right here, and it would store, the value of z, which we would get from value, which would be the result of a load operation, and it would store into a virtual register, and that would go into our destination, which in this case would be z, y, what was it? Y is our destination. So we got a bug. I'll fix it, but do you get the general idea of the LLVM that's supposed to be generated for statements like that? Okay, I'll show you the test that I wrote. So yeah, that's the one we saw earlier. Scripts run examples test 10. Test 10. So prints out 3 for all these. That's good. Prints out 5. Prints out 19. We got it. We're cool. Yes. Okay. Are there any questions? Any qualms? Are you concerned with any changes I've made up to this point? Not yet. Okay. Well, that is it. That is the whole lecture. So, thanks for coming. Next lecture is probably going to be fixing functions and doing pointer offsets. So, we'll have access to the C standard library at the end of the next lecture. Obviously, we will only have access to things that use integers, which is frustrating, but we can build in a print int function that does what we've been doing this entire time. So, cool. Thanks y'all for watching.
Free lecture.
done with the like and